All right. For our next talk, let's welcome Diego Rojas, who's going to tell us about effective convergence notions for measures on the real line.
Thank you, Joe, and thank you for the organizers for allowing me to speak about this research. It's tied to my thesis work, and it's going to be on defining effective convergence notions for sequences of measures on the real line. So part of this is going to be joint work with my advisor, Tim McNichol. And yeah, without further ado, let's get started. So here's a brief outline of my talk. I'm going to give some background, define the classical versions of weak-conveyed convergence, go over some computable analysis and computable measure theory. Then I'm going to go over each of the definitions, each of the effective definitions for weak and vague convergence of measures on the real line. I'm going to give some results in each of the respects. And then at the end, I'm going to connect both weak and vague convergence of measures. So some background. So let's define the classical version of weak and vague convergence of measures. So if we let M of R be the space of finite Borel measures on R, and we take a sequence mu sub n in MR, then let's take a look at the limit of these integrals. So we're looking at the integral over R of a function f with respect to mu n. That limit tends to the integral over R of f with respect to mu. Now, this f depends, is going to change depending on which convergence notion we use. So for weak convergence, f is going to be a bounded continuous function on the reals. In contrast, vague convergence is going to be a continuous function with compact support. Now, the support in this case is going to be the closure of the set of points at which f attains a non-zero value. Now for some computable analysis. So recall that a computable metric space is a triple with the following properties. You have XD being a complete separable metric space, then S a countable dense subset of R with enumeration given by SI, and then we can compute the distance between any 2 points in S uniformly in their indices. So some examples include the reals with Euclidean distance and the rationals. This is countable dense subset. And then we also have 2 to the omega with the usual Cantor distance and the set of cylinders as the countable dense subset. So now throughout the talk, we will focus on the case when X is the real line. So a Cauchy name of a real number X is a computable sequence of rationals so that they converge, their distances converge really quickly. So this is called the Fash-Cauchy sequence. And we say that a function is computable if it's a function on the reals. It's computable if there's a Turing functional that sends a name of X in the domain of F to a name of F of X. Whenever I say a name of a real, it's always going to be implied to be a Cauchy name. Now, another way of talking about functions, continuous functions on the reals in particular, is by using what's called a compact open name. And so a compact open name of a function f, of a continuous function f on the reals, is an enumeration of the set Nij where f is in Nij. Now, what is Nij? So you take a compact interval I and an open interval j, and they have rational endpoints in each case. And then you define Nij to be the set of continuous functions f on the reals so that the image of I under f is contained in j. So this creates a subbasis for the compact open topology on C of R, which is separable and metrizable. And now a function from continuous functions on the reals to the reals is computable if there's a Turing functional that sends a name, in this case a compact open name of f in the domain of capital F, to a name of capital F of F. So now if we take an effective enumeration of the rational open intervals of R, we define an open set to be sigma 0, 1 if the set of indices for all the rational open intervals that are contained in U is CE, and we denote it by sigma 0, 1 of R. Similarly, for a closed set C, we say that it's pi 0, 1 if the set of indices of the rational open intervals that avoid C is CE, and we denote it by pi 0, 1 of R. Now, we can create indices. If we take an effective enumeration of the CE sets, we can call an index E of U to be when the corresponding index set for U is the each C set. And E is going to be an index of C in pi 0, 1 of R if the corresponding set of indices is also the EC set. So now we will, since we're considering Weil convergence, we also want to talk about compact subsets of R. So we have a naming system for these. So a minimal cover name of K is an enumeration of all minimi finite open covers of K. So remember that a compact set is just for every open cover, there's a finite subcover, and in particular, there's a minimal finite subcover. So if you remove a rational open interval away from, in this case, we're going to work with rational open intervals. But in any case, if you remove an open set from this cover, then it's no longer a cover for K. So K is computably compact if it has a computable name, and we define an index of K to be an index of a name of K. So now for computable measure theory. So a measure mu on the a finite Borel measure mu in R is computable if the measure of the real line is a computable real number and the measure of a sigma 0,1 subset of R is left CE uniformly from its index. And a sequence in MR is uniformly computable if each of the measures is computable uniformly in N. So now we also want to define other special classes of subsets of R in relation to a finite Borel measure. So we say that a set A, subset of the real line, is mu almost decidable if there's a pair of sigma 0,1 subsets of R, U and V, which we call a mu almost decidable pair, such that they're disjoint. The measure of their union is the measure of the whole real line. The union is dense, and A is sandwiched between U and the complement of V. So we're going to define an index E of a mu almost decidable A to be an index of its mu almost decidable pair. Now, for finite Borel measures on the real line, we can define a distance between them. In this case, we're going to give it by the Prokhorov metric. There's another metric that you can use, but in this case, we're going to focus on the Prokhorov metric. So rho, the Prokhorov metric between the Prokhorov distance between mu and nu is going to be the infimum over all epsilon greater than 0, so that mu of A is less than or equal to nu of the epsilon ball around A plus epsilon, and nu of A is less than or equal to mu of the epsilon ball of A plus epsilon for all Borel subsets of R. This X should be R. So yeah, this is the Borel sigma algebra of R, and then, as I said, this is going to be the epsilon neighborhood of A, which is defined as the union over all the open balls of radius epsilon around A for every A in capital A. So some work by Mateo Hoyrup and Cristo Rojas gives us the following. So the finite Borel measures on the real line with the Prokhorov metric and the countable dense subset being the space of finite rational linear combinations of Dirac measures on R forms a computable metric space. And a measure is computable if and only if the integral is computable on computable continuous functions on the reals uniformly from a name of F. So now, with this information, we can get started on defining the effective, the frameworks for the effective theory of weak and Weil convergence of measures. So let's start with effective weak convergence of measures. So take a sequence mu sub n in M of R. So now we say that it effectively weakly converges to mu if for every bounded computable function f, the limit of the integrals is going to be equal to the integral of f with respect to mu. And it's possible to compute an index of a modulus of convergence for the sequence of integrals against the measures in your sequence from an index of f and a bound b on the absolute value of f. Now, as you can see, this definition is non-uniform. It's gonna depend on the index for your computable function, and it only is able to you're only able to test the convergence on bounded computable functions. So instead, we also define a uniform version of this. So mu of n uniformly effectively weakly converges to mu. If it weakly converges to mu, and there's a uniform procedure that computes for any bounded continuous function f a modulus of convergence for the sequence of integrals from a name of f and a bound b on the absolute value of f. So the difference between these two in particular, apart from the uniformity, is that this definition directly implies the classical definition of weak convergence. This one doesn't do it directly because, as you can see, you're only able to do stuff with computable functions, whereas in this case, you can use any bounded continuous function. So now some examples. If you take two rationals A and B, you can define this sequence and a uniform computable sequence Q sub n of rationals that decreases to 0. You can define this sequence mu n of E, which is just Lebesgue measure of E intersect the closed boundary interval A minus Qn to B plus Qn. That effectively weakly converges to the Lebesgue measure of E intersect the closed interval AB. And now for a uniformly computable sequence R of n in the rationals that converges to some computable real number, the sequence of point masses on those rationals effectively weakly converges to the point mass at the limit. So now, if your measure is uniformly computable and effectively weakly converges to a measure mu, then that measure has to be computable. And and that gives us a way to distinguish between classical and effective weak convergence of measures. So let me give you this non-example of an effectively weakly convergent sequence, or rather one that is not. So if you take a uniformly computable increasing sequence of rationals that converges to an incomputable less C real alpha, then the Lebesgue measure of E intersect the interval from 0 to Qn weakly converges in the classical sense to the Lebesgue measure of E intersect the interval from 0 to alpha, but it fails to effectively weakly converge since the measure of the real line is not a computable real number. So there are other examples of sequences. One which you can find is related to cellular automata, but we're not going to go over those. I just wanted to give this quick example just to have a general idea of how to distinguish between classical and effective weak convergence. So now we also in a preprint that's available on the archive, I'll post a link at the end of this slide. With my advisor Tim McNichol and we showed that for a uniformly computable sequence of measures, effective weak convergence and uniformly effective weak convergence are equivalent. And the way that you do this, one is from 2 to 1 is pretty straightforward, but from 1 to 2, you essentially want to run an approximation on a closed bounded interval. So like you make the complement very small, the measures of the complements very small for each of the measures. And then you want to do an approximation procedure on the inside of a closed bounded interval, where now you can compute a rational polygonal function that approximates f really well. So those are some properties. And now, once we have this effective version of weak convergence, our next goal is to define to prove an effective version of a characterization theorem in classical weak convergence called the Portmanteau Theorem, which is a theorem originally by Alexandrov, proven in 1941. So this Portmanteau Theorem goes as follows. So for a sequence mu of n in M of R, the following are equivalent. Mu of n weakly converges to mu is equivalent to saying that for every uniformly continuous function f that's bounded on the reals, you get the integral the limit condition on the integrals. Then for every closed subset of R, the lim sup of the mu n measure of C is bounded above by the measure mu, the mu measure of C. That's also equivalent to saying that for every open subset of R, the lim inf of the mu measures of U is bounded below by the mu measure of U. And now for every mu continuity subset A of R, a mu continuity subset is just a subset whose boundary has measure 0. The limit as n approaches infinity of the mu n measures of A is going to be equal to mu of A. So the way that we're going to create an effective version of this theorem, we're going to first need a few definitions. Well, it can be summarized in this definition. So we're going to be working with what are called computable witnesses. So suppose you have a sequence of real numbers a sub n, and you have a function that takes an irrational and outputs a natural number. So we say that G witnesses that the lim inf of the ANs is not smaller than A if the domain of G is the left Dedekind of A, and R is less than AN whenever R is in the domain of G, and N is greater than or equal to G of R. And we define analogously a witness that the lim sup of the ANs is not larger than A if now instead the domain of our function is the right Dedekind of A, and R is greater than or equal to AN whenever R is in the domain of G, and N is greater than or equal to G of R. So in this way, if you have a computable witness that the lim inf of the sequence is not smaller than your limit, and the lim sup of your sequence is not larger than your limit, if you have those two computable witnesses, then you can form a computable modulus of convergence for your sequence that tends to that limit A. So this is an effective version of the lim inf and lim sup. So we're going to use that to, yeah, you have a question? Oh, okay. So we're going to form a computable version of this Portmanteau theorem. So if you have a uniformly computable sequence of measures in M of R, you have the following equivalence. So mu n effectively weakly converges to mu is equivalent to saying that from indices E and B, so that E indexes a computable, a uniformly continuous F that's also bounded with its bound being B, it's possible to compute a modulus of convergence of the sequence of integrals with the limit being naturally the integral of over R of F with respect to mu. Now, 3, 4, and 5 are going to be the effective versions of the conditions on the values on the sets. So the limit is computable, and from an index of a pi0 1 subset C, it's possible to compute an index of a witness that the lim sup of the mu n of C's is not larger than mu of C. Now, also, that's the same thing as saying that mu is computable, and you can do this the same thing with an index of a sigma 0 1 subset of R, but now instead you can compute an index of a witness that the lim inf of the mu n measures of U is not smaller than mu of U. And then lastly, mu is computable, and for every mu almost decidable subset A, the limit as n approaches infinity of mu n of A is equal to mu of A, and you can compute from a mu almost decidable index of A an index of a modulus convergence for the sequence of the mu n of A's. So in this case, we can do this because for computable measures, for a computable measure mu, the mu measure of an almost decidable subset is going to be a computable real number. So now this is a formulation for the effective Portmanteau theorem, and we can also do something similar. We can also get an equivalence by looking at an effective convergence in the Prokop metric. So we say that mu of n converges effectively in the Prokop metric rho introduced earlier in the talk if there's a computable function on the naturals, so that n greater than or equal to epsilon n implies that the rho distance between mu n and mu is less than 2 to the minus n for all n and capital N. So as I said earlier, rho metrizes the topology of reconvergence on mx for a separable metric space X, and you get the following result, which is a consequence of the effective Portmanteau theorem. So for a uniformly computable sequence in M of R, the following are equivalent: effective weak convergence and effective convergence in the Prokop metric are equivalent for any computable sequence of measures. So This is all for effective weak convergence. And now a more interesting mode of convergence is going to be effective vague convergence of measures on the reals. So we're going to use similar definitions, but instead, since we're not guaranteed since we're not necessarily looking for a bound, we're going to use the support of F to define our effective vague convergence. So how do we do this? A sequence mu(n) effectively vaguely converges to a measure mu if for every compactly supported computable function f on the reals, you get the limit condition on the integrals, and it's possible to compute an index of homogeneous convergence for the sequence of integrals from an index of f and an index of the support of f. So now we're using the support of f, an index of the support of f, to give us a way to compute an index of homogeneous convergence for the sequence of integrals. And again, this is also non-uniform, and it doesn't directly imply the classical version of vague convergence. On the other hand, we also have a uniform definition, which we say that a sequence uniformly effectively vaguely converges to mu if it vaguely converges to mu, and there's a uniform procedure that computes for any compactly supported continuous function f a modulus of convergence for the sequence of integrals from a name of f and a name of the supreme of the support of f. So remember that for the name of f, that's going to be a compact open name, and the name of the support of f is going to be a minimal cover name of the support of f. Since it's compactly supported, so the support is going to be compact. So now here's some properties. Now you would think that the limits for effective vague convergence are also computable, but I'm here to tell you the bad news, or rather the interesting news, that it's not necessarily the case. So you can form a uniformly computable sequence of measures in MR that effectively vaguely converges, but such that the limit measure mu has the property that mu of R is an incomputable real. So how do we do this? Well, with spectral sequences, because spectral sequences are nice sequences that give us interesting counterexamples. So take your favorite incomputable CE set, and you get an effective enumeration of A. So now the sequence defined by the sum from I equals 0 to n of 2 to the minus ai plus 1 times the point mass at I for each n, that effectively vaguely converges to the measure mu given by the sum from I equals 0 to infinity of 2 to the minus ai plus 1 point mass at I. So as you can see, the limit, the measure of the real line is going to be the limit of a spectral sequence. So that's an incomputable real. And the way to compute an index of homogeneous convergence is to take the maximum of, so you start out with an index of the support of a compactly supported continuous function. And then you compute its maximum, you take the ceiling, and you add 1. That's going to define an index of homogeneous convergence for the sequence of integrals. So you're guaranteed effective vague convergence. So we found this to be a very interesting example of how the vagueness in the classical sense also provides a vagueness for in the computable sense for this convergence notion on sequences. But if you have a uniformly computable sequence that effectively vaguely converges to mu, and the measure of R is computable, then now you're guaranteed to have a computable limit. And so the equivalence for effective weak and uniformly effective weak convergence also follows in the effective vague convergence sense. So effective vague convergence is equivalent to uniformly effective vague convergence. And in fact, the proof of this theorem is easier than the proof for weak convergence because, well, the approximations for are, you can approximate a closed boundary interval by what looks like a tent, and that's going to be compactly supported. So the proof actually follows more nicely. And now to finish up, I want to make a connection, provide a condition that makes effective vague and weak convergence equivalent. So now if you have a uniformly computable sequence of measures, and you suppose further that there's a computable modulus of convergence for the sequence of mu(n) measures of R, then effective vague convergence for the sequence is equivalent to effective weak convergence. And as a corollary, we get an effective version of the classical result in probability theory, which is, in the classical sense, a sequence of probability measures vaguely converges if and only if it weakly converges. And in this case, if you have a uniformly computable sequence of probability measures, then it effectively vaguely converges if and only if it effectively weakly converges. So that being said, it looks like I'm out of time. So I've provided some references, and in the last link here, you'll see the archive for the preprint of the effective notions of weak convergence of measures on the real line with Tim McNichol. And that being said, thank you.
Are there any questions?
So I'd like to ask maybe a vague question or a weak question, but thinking just about the weak version, say, so you've proved a number of equivalences.
Yes.
And then you prove both the notions of convergence and then the Portmanteau versions. Have you thought about the question of what you need to prove these equivalences, either in terms of reverse mathematics or computational procedures? And if so, does this give you some handle on the complexity of proving the classical theorems?
So that's an interesting question that I've been thinking about. Right now, I'm currently focused. I'm more focused on developing the theory in itself before looking at the complexity. So I'm starting out with looking at what happens on the real line, and then trying to generalize it for any computable metric space, and then that'll allow me to get a better picture of the complexity of how to prove these theorems and what set of axioms are required to prove these theorems. But yeah, that's an interesting question. I'd like to see if I can do any if I can prove from RCA not any of these statements, and that can give me like a better picture of what you need for the Portmanteau theorem to prove the classical Portmanteau theorem.
Yeah, that's exactly the idea. Is that if you could figure out what it takes to prove the effective version, you could lift it to the classical one and maybe get some new kinds of results there.
Yeah, that'll be interesting. Thank you very much. Yeah.
Thank you.
More questions? If not, let's thank Diego again.
Thank you.